Hello and welcome. In this video, we will explore the geometry of planes in three-dimensional space. By the end of this session, you will be able to, first, understand the different ways three planes can be arranged in space. Second, use row operations to solve systems of three linear equations with three variables. And third, interpret the solutions geometrically, connecting the algebra to the visual arrangement of the planes. These skills are fundamental for the IB Mathematics Analysis and Approaches higher-level curriculum. Let's begin by considering the possible arrangements of three planes in space. There are 8 distinct geometric scenarios. First, all three planes can be coincident, meaning they are the exact same plane. This results in infinitely many solutions, as every point on the plane satisfies all three equations. Second, two planes can be coincident, and the third plane intersects them. The solution is the line of intersection, which means infinitely many solutions. Third, two planes can be coincident, and the third plane is parallel to them. In this case, there is no intersection, and therefore no solution. Fourth, two planes can be parallel, and the third plane intersects both of them. This creates two parallel lines of intersection, so there is no common point of intersection, and thus no solution. Fifth, all three planes can be parallel. Clearly, they will never intersect, so there is no solution. Sixth, the three planes can intersect at a single, unique point. This is the most straightforward case, resulting in exactly one solution. Seventh, the three planes can intersect along a common line. This means there are infinitely many solutions, as every point on that line satisfies all three equations. And eighth, the line of intersection of any two planes can be parallel to the third plane. This forms a triangular prism shape, where the three lines of intersection are parallel but never meet at a common point. Therefore, there is no solution. So to summarize, we can have a unique solution, infinitely many solutions, or no solution. Our goal is to use algebra to determine which of these cases applies to a given system of equations. To determine the relationship between planes, we need to solve a system of linear equations. We'll use a powerful method called row operations on an augmented matrix. Let's look at our first example. We have the system x plus 3, y minus z equals 15, 2x plus y plus z equals 7, and x minus y minus 2z equals 0. First, we write this system as an augmented matrix. The coefficients of x, y, and z form the left side, and the constants form the right side. This gives us the matrix. Row 1 is 1, 3, minus 1, 15. Row 2 is 2, 1, 1, 7. And row 3 is 1, minus 1, minus 2, 0. Our goal is to transform this matrix into row echelon form, where we have ones on the main diagonal and zeros below them. We do this using three types of row operations: swapping two rows, multiplying a row by a non-zero scalar, and adding a multiple of one row to another. Let's start by making the first element in the second row 0. We can do this by subtracting 2 times the first row from the second row. We also want to make the first element in the third row 0, so we subtract the first row from the third row. Performing these operations, our matrix becomes: row 1 is unchanged, row 2 is 0, minus 5, 3, minus 23, and row 3 is 0, minus 4, minus 1, minus 15. Next, we want to make the second element in the second row a 1. We can achieve this by multiplying the second row by negative 1/5. This gives us row 1 is unchanged, row 2 is 0, 1, minus 3/5, 23/5, and row 3 is unchanged. Finally, we make the second element in the third row 0. We can do this by adding 4 times the new second row to the third row. This results in our row echelon form. Row 1 is unchanged, row 2 is unchanged, and row 3 is 0, 0, minus 17, 17. Now we can use back substitution to find the solution. The last row represents the equation minus 17z equals 17. Solving for z, we find that z equals minus 1. The second row represents the equation y minus 3/5 z equals 23/5. Substituting z equals minus 1, we get y plus 3 divided by 5 equals 23/5, which simplifies to y equals 4. The first row represents the equation x plus 3 y minus z equals 15. Substituting y equals 4 and z equals minus 1, we get x plus 12 plus 1 equals 15, which means x equals 2. So we have a unique solution. X equals 2, y equals 4, and z equals minus 1. Geometrically, this means the three planes intersect at a single point, 2, 4, minus 1. This corresponds to case 6 from our list. Now let's examine a case with infinitely many solutions. This occurs when the planes intersect in a line. Consider the system 2x minus y plus z equals 5, x plus y minus z equals 2, and 3x minus 3, y plus 3z equals 8. Again, we start by writing the augmented matrix. The matrix is, row 1 is 2, minus 1, 1, 5. Row 2 is 1, 1, minus 1, 2, and row 3 is 3, minus 3, 3, 8. It's often helpful to have a 1 in the top left corner. Let's swap the first and second rows. After swapping, the matrix is, row 1 is 1, 1, minus 1, 2, row 2 is 2, minus 1, 1, 5, and row 3 is 3, minus 3, 3, 8. Now, we make the first elements in the second and third rows 0. We subtract 2 times the first row from the second and 3 times the first row from the third. This gives us, row 1 is unchanged. Row 2 is 0, minus 3, 3, 1, and row 3 is 0, minus 6, 6, 2. Notice that the third row is exactly 2 times the second row. This is a strong indicator of infinitely many solutions. Let's continue to row echelon form. We can multiply the second row by negative 1/3 to get a 1. Then, we subtract 2 times the new second row from the third row. This makes the third row all zeros. The row of zeros indicates that the system has infinitely many solutions. To describe them, we introduce a parameter. Let's set z equal to t. From the second row, we have y minus z equals negative 1/3. Substituting z equals t, we get y equals t minus 1/3. From the first row, we have x plus y minus z equals 2. Substituting our expressions for y and z, we get x plus t minus 1/3 minus t equals 2. The t's cancel, leaving x equals 7/3. So the solution is x equals 7/3, y equals t minus 1/3, and z equals t, where t is any real number. This is the parametric equation of a line. Geometrically, the three planes intersect in this common line. This is case 7. Finally, let's see what happens when there is no solution. This is called an inconsistent system. Consider the system. X plus 2 y minus z equals 6, 2x plus 4 y plus kz equals 12, and x plus 3 y minus z equals 2. Let's write the augmented matrix. The matrix is, row 1 is 1, 2, minus 1, 6, row 2 is 2, 4, k, 12, and row 3 is 1, 3, minus 1, 2. Let's perform row operations to get to row echelon form. We subtract 2 times the first row from the second and the first row from the third. This gives us, row 1 is unchanged, row 2 is 0, 0, k plus 2, 0, and row 3 is 0, 1, 0, minus 4. Let's swap the second and third rows to get a 1 on the diagonal. The matrix is now, row 1 is unchanged, row 2 is 0, 1, 0, minus 4, and row 3 is 0, 0, k plus 2, 0. Now, let's analyze the third row, which represents the equation k plus 2 times z equals 0. If k is not equal to minus 2, then we can divide by k plus 2, which means z must be 0. The second row gives y equals minus 4, and the first row gives x equals 14. This is a unique solution, case 6. Now, what if k equals minus 2? The third row becomes 0, z equals 0. This equation is true for any value of z. This means z is a free variable, so we have infinitely many solutions. From the second row, y equals minus 4. From the first row, x minus 8 minus t equals 6, so x equals 14 plus t. The solution is a line, case 7. This example shows how a parameter can change the nature of the solution. We've seen how to find a unique solution, infinitely many solutions, and how to identify the conditions for each. Let's work through another example that involves a parameter, as these are common in IB exams. Consider the system: x plus y plus 3, z equals 2, 3x minus y plus 2, z equals 5, and 5x plus y plus 8z equals a. We'll reduce this to row echelon form and then analyze the result based on the value of chara a. The augmented matrix is: row 1 is 1, 1, 3, 2, row 2 is 3, minus 1, 2, 5, and row 3 is 5, 1, 8a. First, we subtract 3 times the first row from the second, and 5 times the first row from the third. This gives us: row 1 is unchanged, row 2 is 0, minus 4, minus 7, minus 1, and row 3 is 0, minus 4, minus 7, a 10. Now let's make the second element in the second row 1. We multiply the second row by negative 1/4. This gives us: row 1 is unchanged, row 2 is 0, 1, 7/4, 1/4, and row 3 is unchanged. Finally, we make the second element in the third row 0. We add 4 times the new second row to the third row. This results in: row 1 is unchanged, row 2 is unchanged, and row 3 is 0, 0, 0, a 9. The third row represents the equation 0, z equals a 9. The solution depends entirely on the value of chi a. If a is not equal to 9, the equation becomes 0 equals a 9, which is a contradiction. This means the system is inconsistent and has no solutions. Geometrically, this corresponds to case 8, where the line of intersection of two planes is parallel to the third. If a equals 9, the equation becomes 0 equals 0, which is always true. This means z is a free variable and we have infinitely many solutions. Let z equal t. From the second row, y plus 7/4 t equals 1/4, so y equals 1 to 7t slash 4. From the first row, x plus 1 to 7t slash 4 plus 3t equals 2, which simplifies to x equals 7 to 5t slash 4. This is the parametric equation of a line, case 7. This example clearly shows how a single parameter can determine whether a system has no solution or infinitely many solutions. Let's tackle a more complex problem involving 3 mutually perpendicular planes. This requires a good understanding of normal vectors. We are given 3 planes, P1, P2, and P3, which are mutually perpendicular. Their equations are given with unknown constants a, b, and c. The key property here is that if 2 planes are perpendicular, their normal vectors are also perpendicular. This means their dot product is 0. The normal vector for a plane in the form ax plus bi plus cz equals d is simply the vector of coefficients, a, b, c. So, the normal vectors for our 3 planes are n1 equals a, 3 minus 1, n2 equals b, 0, 2, and n3 equals c, minus 5, minus 3. Since the planes are mutually perpendicular, the dot product of any 2 normal vectors must be 0. Let's start with n1 and n2. Their dot product is a times b plus 3 times 0 plus minus 1 times 2, which equals ab dash 2. Setting this to 0 gives ab equals 2. Next, n1 and n3. Their dot product is a times c plus 3 times minus 5 plus minus 1 times minus 3, which equals ac1 5 plus 3, or ac12. Setting this to 0 gives ac equals 12. Finally, n2 and n3. Their dot product is b times c plus 0 times minus 5 plus 2 times minus 3, which equals bc-6. Setting this to 0 gives BC equals 6. We now have a system of 3 equations with 3 variables. AB equals 2, AC equals 12, and BC equals 6. We can solve this by multiplying the 3 equations together. Multiplying them gives a squared b squared c squared equals 144. Taking the square root, we get ABC equals plus or minus 12. The problem states that a, b, and c are positive constants, so we must have ABC equals 12. Now we can find each constant. Since BC equals 6, we substitute into a, BC equals 12, to get a times 6 equals 12, so a equals 2. Since a, c equals 12, we get b times 12 equals 12, so b equals 1. And since ab equals 2, we get 2 times c equals 2, so c equals 1. Wait, I made a mistake in the calculation. Let's recheck. ABC equals 12. If BC equals 6, then A6 equals 12, so A equals 2. If AC equals 12, then B12 equals 12, so B equals 1. If AB equals 2, then 2, 1, C equals 12, so C equals 6. My apologies. The correct values are A equals 2, B equals 1, and C equals 6. So, the correct values are A equals 2, B equals 1, and C equals 6. This problem demonstrates how geometric properties can be translated into algebraic equations to find unknown parameters. Let's conclude with a problem that combines lines and planes, a common theme in vector applications. We are given a plane pi1 with the equation x minus 2y plus 4, z equals 21, and a line L with vector equation r equals 3 minus 1, 4, plus t times 6, 1, minus 1. Part A asks us to show that the plane pi1 contains the line L. For a plane to contain a line, 2 conditions must be met. First, a point on the line must lie on the plane. Second, the direction vector of the line must be perpendicular to the normal vector of the plane. From the line's equation, we can identify a point on the line, P3, minus 1, 4, and its direction vector d equals 6, 1, minus 1. From the plane's equation, its normal vector is n equals 1, minus 2, 4. Let's check the first condition. We substitute the coordinates of point P into the plane's equation. We get 3 minus 2 times minus 1 plus 4 times 4, which equals 3 plus 2 plus 16, which is 21. Since 21 equals 21, the point P lies on the plane. Now for the second condition. We check if the direction vector d is perpendicular to the normal vector n by calculating their dot product. d dot n equals 6 times 1 plus 1 times minus 2 plus minus 1 times 4, which is 6 minus 2 minus 4, which equals 0. Since the dot product is 0, the vectors are perpendicular. Both conditions are met, so the plane pi1 contains the line L. Part B asks for the point where the line L intersects a second plane, pi2, with equation 5x minus y plus 3z equals 2. To find the intersection, we need to find the value of the parameter t for which a point on the line also satisfies the plane's equation. First, we write the parametric equations for the line L, x equals 3 plus 6t, y equals minus 1 plus t, and z equals 4 minus t. Now, we substitute these expressions for x, y, and z into the equation for plane pi2. This gives us 5 times 3 plus 6t minus 1 plus t plus 3 times 4t equals 2. Expanding and simplifying, we get 15 plus 30t plus 1 minus t plus 12 minus 3t equals 2. Combining like terms, we have 28 plus 26, t equals 2. Solving for t, we find t equals minus 1. To find the coordinates of the intersection point, we substitute t equals minus 1 back into the parametric equations of the line. This gives x equals minus 3, y equals minus 2, and z equals 5. So the line L intersects plane pi2 at the point minus 3, minus 2, 5. Part C asks us to find the angle between the line L and the plane pi2 and the angle between the two planes, pi1 and pi2. Let's start with the angle between the line L and the plane pi2. The formula for this angle, theta, is given by the sine of theta equals the absolute value of the dot product of the direction vector of the line and the normal vector of the plane, all divided by the product of their magnitudes. We already know the direction, vector d equals 6, 1, minus 1. The normal vector for pi2 is n2 equals 5, minus 1, 3. First, let's calculate the dot product. D dot n2 equals 6 times 5 plus 1 times minus 1 plus minus 1 times 3, which is 30 minus 1 minus 3, or 26. Next, we find the magnitudes. The magnitude of D is the square root of 38. The magnitude of n2 is the square root of 35. Plugging these values into the formula, we get sine of theta equals 26 divided by the square root of 38 times the square root of 35. Taking the inverse sine, we find the angle theta is approximately 47.5 degrees. Now let's find the angle between the two planes, pi1 and pi2. The angle between two planes is the same as the angle between their normal vectors. We use the dot product formula for vectors. Cosine of the angle phi equals the absolute value of the dot product of the normal vectors divided by the product of their magnitudes. We know n1 equals 1 minus 2, 4, and n2 equals 5 minus 1, 3. Their dot product is 1 times 5 plus minus 2 times minus 1 plus 4 times 3, which is 5 plus 2 plus 12, or 19. The magnitude of n1 is the square root of 21. The magnitude of n2 is the square root of 35. So cosine of phi equals 19 divided by the square root of 21 times the square root of 35. Taking the inverse cosine, we find the angle phi is approximately 27.8 degrees. Let's recap what we've covered. We started by visualizing the 8 possible geometric arrangements of 3 planes in space. We then learned how to use row operations on an augmented matrix to solve systems of 3 linear equations. We saw how the final row echelon form tells us whether there is a unique solution, infinitely many solutions, or no solution. We worked through examples of each case, including those with parameters, and connected the algebraic results directly to their geometric interpretations. Finally, we practiced finding angles between lines and planes, and between two planes, using dot products of direction and normal vectors. You are now equipped to tackle a wide range of problems involving planes and systems of equations, which are key components of the IBAAHL syllabus. Thank you for watching. To solidify your understanding, here are 5 practice questions in the style of IB assessment. Pause the video, work through them, and then resume to see the fully worked solutions. Question 1. Solve the system of equations and interpret the solution geometrically. Question 2. Find the value of k for which the system has no solution. Question 3. Find the angle between the line and the plane. Question 4. Find the Cartesian equation of the plane containing 3 given points. And question 5. Find the shortest distance between 2 skew lines. Welcome back. Let's go through the solutions. For question 1, we set up the augmented matrix and perform row operations. We find that the system is inconsistent, leading to a contradiction. Geometrically, this means the 3 planes do not intersect at a common point. This could be case 4, 5, or 8. For question 2, we reduce the matrix to row echelon form. The third row becomes 0 equals 4. This is a contradiction, so there is no solution. The value of k does not affect this outcome. Geometrically, the first 2 planes are parallel, and the third plane is not parallel to them, so there is no common intersection. For question 3, we use the formula for the angle between a line and a plane. We find the dot product of the direction vector and the normal vector, and their magnitudes. The sine of the angle is 1 divided by the square root of 6 times the square root of 14. The angle is approximately 6.0 degrees. For question 4, we find 2 vectors in the plane, A, B, and AC. Their cross product gives us the normal vector to the plane. Using the normal vector in one of the points, we find the Cartesian equation of the plane is x plus 3y plus 2z equals 5. For question 5, we first show the lines are skew. Then we find the common perpendicular vector by taking the cross product of their direction vectors. The shortest distance is the absolute value of the dot product of a vector connecting the two lines with the unit common perpendicular vector. The distance is 3 divided by the square root of 14. Thank you for watching this video on the geometry of planes and systems of linear equations. I hope this rigorous and detailed explanation has been helpful for your IB Mathematics AAHL studies. Keep practicing these techniques to build your confidence and mastery.